A widely accepted hypothesis in conventional cosmology states that the beginning of the universe is everywhere and nowhere. Therefore, cosmologists do not consider a center for the universe and believe that no point in the universe has precedence over another. However, contrary to the conventional cosmological theory, t-consciousness cosmology proposes a single central point for the universe from a spatial perspective and has identified a specific point for this centrality, a topic that will be fully covered in another episode. This hypothesis also addresses the centrality of each particle in the universe from a particular perspective, stating that each particle can be considered the center of the universe from a temporal point of view. The observer and general centrality of particles. The T-Consciousness Cosmology documentary series, Episode 6. The universe we observe is not exactly as we see it. The position of stars and galaxies is much different from the images we recognize. For example, the galaxy we see here, its light reaches us from this angle after winding through space, while the galaxy itself is located elsewhere. The star we see here has died over 1,000 years ago and after undergoing various stages has turned into a black hole, yet we still see it in its stellar era. For us, it is a living star because the light we receive from it belongs to thousands of years ago. Hypothetically, if someone were now 2,330 light-years away from Earth and observed our planet, they would be able to see the era of Alexander's military campaigns, and he would still appear alive and well. The different physical conditions of the environment and the reference frame of the observer can also change the image in front of the observer. In physics, a reference frame is a framework in which an observer is situated and based on which they make observations and measurements. For instance, an observer gazing into the depths of space from the moon sees a very different image of the stars compared to an observer on Earth. This is because the moon's atmosphere is much thinner and light doesn't scatter as much, causing the light from celestial objects to be dispersed only in one direction, from the perspective of the observer on the moon. An observer moving at speeds close to the speed of light, compared to an observer at rest, would no longer see the light of celestial objects around and behind them, and would only see a bright aperture in front of them. However, an observer near a black hole would perceive the image of objects around the black hole differently. By examining these examples, we arrive at two important conclusions. First, each observer, based on their reference frame and the physical conditions of their environment, observes different images of cosmic events. Second, every observer always sees the past of the cosmos, not its present state. From the perspective of t-consciousness cosmology, we encounter two types of observers: general observer and special observer. A general observer is one who continuously monitors its environment and can interact with its surroundings such that it reacts to the conditions when they become favorable. As a result, all constituents of the cosmos, from the most fundamental particles to living beings and the largest cosmic structures, are considered observers of their environment. However, a special observer, in addition to having the conditions of a general observer, has the ability to analyze the scenery and can delve into the nature of what they observe around them. This observer is none other than humans. Therefore, the main observer is the human who observes the constituents of the cosmos, either with a naked eye or with the aid of observational instruments. Despite the relatively stable system for measuring time, various fields such as science, philosophy, religion and art have each offered different definitions of it. In recent centuries, timepieces have displayed moments based on seconds, minutes, and hours. Yet the basis of these units has evolved over history. In particle physics, time is expressed in terms of energy, and in the theory of relativity, time dilation is represented by a dimensionless value. Now, the question raised by t-consciousness cosmology is, how is it possible that all constituents of the cosmos, from a quantum-sized particle like a cesium atom, for which a second is defined by the precise number of its vibrations in a normal state, to a massive object like a black hole, in each of which time is calculated as a quantitative measure, are simultaneously in motion within a framework known as space-time, where time itself is considered as a dimension. In other words, how does a four-dimensional space-time framework, where time is calculated as a quantity for each particle or wave, merge to form a system? And how is time itself considered as a dimension for the entirety of that system? Does this not create a paradox in which time is both a dimension and a quantity? To explain this concept, t-consciousness cosmology states that the nature and manifestation of time are dependent on gravity. This perspective considers the very existence of energy, which is used in particle physics as a unit to express time, as dependent on objects and waves. This implies that mass without gravity is meaningless. Moreover, the detection and measurement of waves themselves depend on the existence of particles, which by having mass, give rise to gravity. Consequently, time, without particles, is meaningless, and it is also a function of the gravity generated by the particle. Essentially, it is the particle that manifests time, not energy. It's also essential to note that the particle, gravity, and time are intertwined. As soon as a particle comes into existence, time manifests within the particle due to the gravity generated in the surrounding space. In other words, in t-consciousness cosmology, time is a function of the gravity created by the particle, not by space. Therefore, it can be said that time, expressed in terms of energy and particle physics, is in fact a function of the particle that reveals it, and not energy itself. Additionally, from the perspective of t-consciousness cosmology, location is a coordinate resulting from the existence of gravity. Without gravity, the dimensions of length, width, height, or the shape and curvature of the coordinate axis, and even the origin of this axis cannot be defined. In other words, without gravity, space is meaningless. With these explanations, the actual location in space is directly related to gravity. Without gravity, the distance between 2 points becomes undefinable. Since the distance between 2 points is dependent on the passage of time, and time is dependent on gravity, therefore, without the passage of time and the existence of gravity, space becomes meaningless as motion, speed, and the coordinate axis lose their significance. Let's return to the topic of the observed image of the cosmos. Can we observe the present moment of the cosmos? If we could see the present moment of the cosmos, what do you think it would look like? To answer this question, t-consciousness cosmology presents its hypothesis as follows. Suppose, hypothetically, we isolate a particle in the present moment. All the particles surrounding the isolated one would vanish, leaving nothing of the cosmos, because all particles and celestial bodies are relative to the isolated particle in the past. Only this particle exists in the present moment to declare its existence. As a result, this particle, by being isolated by the observer, becomes both the center of the cosmos and the only particle in the cosmos. From the observer's perspective, only this particle is considered definite. In essence, the entire cosmos is condensed into the concept of this particle, and time in the entire cosmos is suspended except for this isolated particle. The key point here is the role of the observer as the isolator of the particle, an integral part of this hypothesis. The observer can isolate any particle, including themselves, quantum particles, or even the largest celestial bodies or cosmic systems. To clarify this hypothesis, let's use an example. Imagine you are that particle in question, floating in space in an astronaut suit. Regardless of how you try to observe your surroundings and become aware of other particles and waves, you need time to pass. However, any information that reaches you is not from that instant, but from the past of that information source. For example, if you are adrift near Earth, the image you see of the sun is about 8 minutes old. Or the information you receive from Earth is a few thousandths of a second old, not its present moment. Any transfer of information requires movement, and movement needs time. Now, if we hold you in the present moment, you will no longer connect with past information, and the past will vanish for you. Without moving from one moment to the next, no movement from the starting point occurs towards anything or anyone. Therefore, you will be the only existing particle in the present moment, and you will not find any trace of other particles in the present. This concept holds true at extremely close distances, even if it requires a billionth of a second to traverse the distance between two particles at the speed of light. Therefore, t-consciousness cosmology states that if we consider the nucleus of an atom to have certainty, meaning we hypothetically isolate it in the present time, the electrons orbiting around it would be subject to uncertainty. Similarly, even if we were to isolate a quark from the inside components of the atom's nucleus in the present time and consider it to have certainty, the other quarks would be subject to uncertainty. This principle would apply to negative ad infinitum within the core of particles. According to t-consciousness cosmology, this ever-present condition is referred to as the Taheri uncertainty principle. In this documentary, the principle is solely addressed from a temporal perspective, but the Taheri uncertainty principle is a broader concept that will be discussed in the future. Therefore, in the present moment and at any given instant, only one particle exists with certainty, while the rest are uncertain. In this matter, the position of the observer is of great significance. Under the Taheri uncertainty principle, two particles cannot be simultaneously placed in the present moment with certainty. Whenever an observer considers one of these particles in the present moment, the other particle relative to the first will be in the past and subject to uncertainty. It is important to note that the Taheri uncertainty principle differs from Heisenberg's uncertainty principle. Heisenberg's uncertainty principle relates to the wave-particle duality, stating that any quantum particle, like an electron or photon, can act either as a wave or a particle, depending on the experimental setup, and is related to the subatomic world. Moreover, one cannot make a definitive assertion on subatomic phenomena based on Heisenberg's uncertainty principle. Since the observer and the measurement instrument are the key to the phenomenon under study. In other words, we can never study or conduct experiments in the atomic world without disturbing it, making the results of different measurements and experiments uncertain. The Taheri uncertainty principle does not only apply to the subatomic world, it also applies to the entire universe. It is for this reason it is known as the Taheri general uncertainty principle in t-consciousness cosmology. The Taheri uncertainty principle asserts that from the observer's perspective, with varying reference frames and physical environmental conditions, every particle in the cosmos can exist in the past, present, or future, demonstrating the dynamism of time. In this view, besides the isolated particle, the temporal states of other particles relative to the isolated one are also considered. For example, if we, as observers, consider particle A with certainty relative to particles B to Z, particle A, while being in the present moment for us as observers, simultaneously represents the future relative to other particles B to Z, which are in the past relative to particle A. Also, if we, as observers, consider one of the particles B to Z with certainty in the present moment, then particle A will be in the past relative to that particle, and the isolated particle we observe will be considered the future for particle A and the rest. The isolated mass can be as small as a single particle, or as large as a galaxy, or even a collection of galaxies. Consequently, all components of that system are isolated together, and objects outside that system are now considered as uncertain. It means that it is impossible to isolate a system and have one of its internal components become uncertain. For instance, if we isolate the solar system, we cannot consider a planet like Jupiter or Venus outside this system, causing them to become uncertain. In other words, all components of the solar system, from the smallest pebbles to the largest planets of the solar system and the Sun itself, are isolated, and the rest of the cosmos, apart from this collection, vanishes. In the spherical cosmos model, the cosmic shell moves from the center of the cosmos towards its terminal edge. In this path, it continuously generates new objects and propels them towards the inside of the cosmos. However, as the cosmic shell moves outward, all objects are also drawn along, towards the terminal edge of the cosmos. This is similar to a person running inside a moving train towards the rear. Despite running in the opposite direction of the train's movement, due to the train's greater speed, the person's innate movement is in the direction of the train's progression. The same applies to newly formed objects in the cosmos. T-consciousness cosmology challenges the Big Bang model by proposing the following scenario. Suppose an observer is located on a galaxy that is younger than the Milky Way and is positioned between our older galaxy and younger galaxies deep in the cosmos. If this observer looks in both directions, towards us and towards the younger galaxies, wouldn't they gain an estimate of their own galaxy's stages of youth and aging? In other words, does observing the depths of space show us past events in the cosmos from the Big Bang to the present? Or does it indicate the formation of new galaxies in the forward expanding process of the cosmos, perceived with a delay due to our spatial location? The response provided by T-consciousness cosmology for this challenge is based on the spherical cosmos model. Observing the depths of space leads us to a vector indicating the direction of the expansion of the cosmos. The initially formed cosmic objects are positioned on one side, while the newly formed objects are seen near the cosmic shell. The direction of this vector can be considered from the past to the future of the cosmos, as the cosmic shell was once at this point, and today it is here, continuously expanding and growing larger. Under these conditions, not only do all cosmic objects follow a time vector moving towards the future, but the cosmos itself is also encompassed by this future-oriented time vector. This contradicts the latest Big Bang model widely accepted by most cosmologists, who state that looking deeper into space is like traveling back in time to the past of the cosmos, like a time machine. However, from the perspective of T-consciousness cosmology, observing the depths of space does not necessarily equate to viewing the past of the cosmos. In other words, according to the mentioned challenge, this viewpoint considers the observation of older galaxies on one side and younger galaxies on the other as evidence for considering a timeline for the aging process of objects from the past to the future in the cosmos, clearly explainable in the spherical cosmos model. This vector can be termed the time continuity vector, which is defined based on the optical information received from observable celestial bodies. For instance, consider an adult woman observing a child on one side and an elderly person on the other. When she looks at the child, she sees an image of her own past or her childhood. And when she looks at the elderly person, she envisions a point she will reach in the future. We can draw a vector for her from the past to the present and from the present to the future, creating a continuity of time. From another perspective, every particle inherently possesses temporal continuity, meaning a transition from past to present and from present to future. Like a middle-aged person who has progressed from infancy to childhood, from childhood to youth, and now from youth to middle age, the future of this person will be a product of their present. According to this view, temporal continuity exists in all elements of the cosmos. In other words, every particle, every living being, and every human, according to the dynamic nature of time, a universal property in the cosmos, is the product of their own past. It is important to note that this theory contrasts with some scientific hypotheses that consider time to be a fixed phenomenon. In general, time itself is relative, according to t-consiousness cosmology. This means that time can be continuous or discontinuous depending on the observer. In other words, if hypothetically, an observer considers a particle in isolated time, then from this perspective, the time for that particle will be discontinuous. This implies that the connection of this particle with its past is severed and it is isolated at a particular moment in time. Another point highlighted by the Taheri uncertainty principle is that this kind of continuity in time both exists and does not exist. In other words, the continuity of time is uncertain. This is because if we chase after every moment in reality, we immediately lose that moment. To simplify this concept, if we divide time within a second into thousands and billions of parts, as soon as we try to capture a present moment, we are unable to reach the fleeting instant of the current moment and transition from one present to another. Every present moment consists of an infinitesimal unit of time. And as observers in the real world, we can never access that one infinitesimal moment of time that constitutes the actual present. The present time only flows within a particle, and outside of its existence, the present time is also relative and uncertain. Considering this, we are faced with the principle of the uncertainty of time, indicating the relative nature of the cosmos. In essence, the entire universe follows the Taheri uncertainty principle.